Algebra 2, 7.1, Graph exponential growth functions. An exponential function has the form y equals a times b to the x, where a cannot equal 0 and the base b is a positive number other than 1. If a is greater than 0 and b is greater than 1, then the function is an exponential growth function. And b is called the growth factor. The simplest type of exponential growth function has the form y equals b to the x. Parent function for exponential growth functions. The function f of x equals b to the x, where b is greater than 1, is the parent function for the family of exponential growth functions with base b. The general shape of the graph of f of x equals b to the x is shown. The x-axis is an asymptote of the graph. An asymptote is a line that a graph approaches more and more closely. So as we go on forever to the left, our graph is going to get closer and closer to the x-axis. The graph rises from left to right, passing through the points 0, 1, and 1b. The domain of f of x equals x to the b is all real numbers, or our all real number symbol, which is an R with two stems. And the range, we never go below the x-axis, so our range is y is greater than 0. Transformations. To graph a function of the form y equals a times b to the x minus h plus k, begin by sketching a graph of y equals a times b to the x. Then translate the graph horizontally by h units and vertically by k units. The y-intercept of the graph f of x equals a times b to the x occurs at 0a. So if there's no number in front, it occurs at 0, 1, which we talked about up here. And if it is another number out in front here, our y-intercept is 0a. Example 1. Graph y equals 4 times 2 to the x minus 1 minus 3. So if we put negative 2 in here, negative 2 minus 1 is negative 3. 2 to the negative 3 is 1/8. 4 times 1/8 is 1/2. 1/2 minus 3, negative 2.5. Negative 1 minus 1 is negative 2, which is 1/4, times 4 is 1, minus 3 is negative 2. 0 minus 1 is negative 1. 2 to the negative 1 is 1/2. Times 4 is 2, minus 3 is negative 1. 1 minus 1 is 0. 2 to the 0 is 1, times 4 is 4, so that's going to be a positive 1. 1 is 2, 8 minus 3 is 5. 16 minus 3 is 13. So we have negative 2, negative 2.5, negative 1, negative 2, 0, negative 1, 1, 1, 2, 5, and 3, 13. Okay, so our graph is going to look like that. So our asymptote is down here. So our domain, is all real numbers, and our range is everything above our asymptote, which is y is greater than -3. Okay. Exponential growth models. When a real-life quantity increases by a fixed percent each year or other time period, the amount y of the quantity after t years can be modeled by the equation y equals a times the quantity 1 plus r to the t power, where a is the initial amount, r is the percent increase expressed as a decimal. Note that the quantity 1 plus r, which is the part inside the parentheses here, is the growth factor. So for example 2 here, in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. Write an exponential growth model giving the number n of incidents t years after 1996. So, n is our number of incidents, so that is our new y. So n equals, then we start with our initial amount, which is our 2573. And then 1 plus our r is 92% written as a decimal, which is 0.92 to the t power. So now, how many incidents were there in 2003? Well, 2003 is 7 years after 1996. So we type in 7 as our exponent. So 2573 times 1 plus 0.92 to the 7th power. And we get 247,485 incidents if we round to the nearest incident. Graph the model on your calculator. Use the graph to estimate the year when there were about 125,000 computer security incidents. So now we're looking for where n equals 125,000, or y equals 125,000. So we're going to type our equation from this part up here into y equals Okay, so now we want to go to window, because we're going to change our window here. Our X min is going to be 0. Our X max can stay at 10, and our X scale can stay at 1. Then our Y minimum is going to be 2,500. Okay, so how I'm getting these, you can't go negative years, so we're starting at 0 here, and we're going to 10 because that's far enough out that we'll get to this. And our scale is 1 because that's how many tick marks there will be. So there will be 10 total tick marks. Then this, our Y minimum here, is less than our initial amount, so we're going to definitely be on the graph without having a bunch of extra space. And our Y maximum, we want to have be bigger than this, so I said 130,000. And then Y scale, I put at 5,000, just so that I wouldn't have a ton of tick marks. So now I'm going to trace on my graph to where I'm at 125,000 or so. And it happens somewhere between 5.9 and 6. We're trying to estimate the year. So 6 years after 1996, so t equals 6. So 6 years after 1996 is 2002. So that is my answer on that. Now, finally, compound interest. Exponential growth functions are used in real-life situations involving compound interest. Okay, just compound interest, not compounded. Okay, compound interest is interest paid on the initial investment, called simple interest, and on previously earned interest. Interest paid only on the principal. This is actually the principal. The initial investment is called the principal, and interest paid only on the principal is called simple interest. So now, consider an initial principal P deposited in an account that pays interest at an annual rate R expressed as a decimal, compounded n times per year. The amount A in the account after t years is given by this equation. A equals P times 1 plus R over n to the n times t power. You deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. So, we are using this equation here, and we're plugging in. So, A equals, our initial amount is $4,000. And then 1 plus our R as a decimal, so I need to move my decimal place twice. So 0.0292 over the number of times per year it is compounded. Quarterly, means it is compounded 4 times a year. And then 4 times the number of years, which is 1. So 4,000 times 1 plus 0.0292 divided by 4 to the 4 times 1 power is $418.09. Round to the nearest penny. And then we're going to use the formula again. So our initial investment is still $4,000. Our interest rate is the same, so 0.0292. Now, daily means we have 365 days in a year. So we are going to use 365 and we get $4,118.52. So the more frequently you compound, the more money you earn.